Hey, welcome back. This is the third video in a series of looking at lines or rings of charge. So the first one was a line of charge, finding an electrical field adjacent to that. Second one was a semicircle of charge and finding the electrical field from that. And this is going to be a ring of charge. Next one will probably be plates of charge, and then yeah, I think I'm done with this. So let's see what we got. So we're going to have a ring of charges. So I'm going to have some charge distributed around the ring, and I want to come up with an equation for any point on this line. So when I get way out to here, that when I get far away, then this should behave like a point charge. And when I get right in the middle here, I'm thinking this is going to be 0, right? So if I have a charge inside here, that's going to be pulled or pushed equally in all directions. So I'm thinking it should be 0 here. We can check to see how we get. So let's set this up. So I'm going to have some point here. Let's make it a distance x away. So this is a point that I'm interested in. It's not a charge. It's just a point in space I'm interested in. I want to find the electrical field. Where's the electrical field coming from? Well, let me think about this. This is coming from this little bit of charge up here, right? And if this is a positive ring, then I'm going to have some sort of distance there. So I'm going to have some electrical field. It's going to be this thick green arrow here. And I'll have some distance here. I don't know what this is. I'll call this R. Right? Let me think about the bottom, though. At the bottom, I'm going to have another bit of charge, and that's going to generate another field along this line. I should use the dashed line. That's better. And I'm going to have some other electrical field coming from this. Right? So two important things to get from this. So one, you might notice that this distance is going to stay the same. So the R here is going to be the same as the R here. So that's going to be consistent. Second thing is that these two are vectors, and some of the vector components are going to cancel. So in this case, the way I've set this up, you can see that the vertical components are going to cancel, and the horizontal component is going to stay there. So this is what I'm worried about. So I'm worried about this angle in here, right, which is just going to be the same as the angle in here, right, or this angle in here. It's all going to be the same. That's because it's a circle, and because of symmetry, I can ignore the vertical components, and I'm only worried about this component that's going to be adjacent to that angle. Right? So adjacent, I am thinking cosine function. Right? So here's what I want to do is I want to come up with some description for my electrical field, and generally my electrical field is going to be some constant 1 over 4 pi epsilon naught. I'll just use K because I can't bother to write that much stuff. That's going to be K times the charge divided by the square of the distance. Right? So I'm going to think about now I'm going to have some small amount of my electrical field that I'm going to add up. So it's going to be K times my small charge dq divided by that distance that it's going to be. Well, this is the thing. I want to get everything in terms of x. Right? And then I want to just take the component that's going to be along the x-axis there, because my vertical components are going to get rid of. So this is what I'm going to do. So I'm going to use the cosine of the angle, right? So if I multiply my little bit of electrical field times the cosine of the angle, right, that's going to give me this horizontal component, which I care about here. So this is going to give me my my component that's pointing in the same direction, so my horizontal component, and in that case, not my vertical component. So I just want that section that's going in the x direction. Here's the thing. So I want to make sense out of this. On dq, I'm not going to worry about in this case. Usually I do worry about that, and I'll use some density function to try to get rid of it. I'm not going to worry about it in this case. You'll see why in just a minute. But r, yeah, that doesn't make sense. I need to get that in terms of x. And cosine function, yeah, that's going to change, right? So as I get further away, my angle is going to change. So I need to have some way of getting this in terms of x. But fortunately, I can make a right triangle here, right? So here's my triangle. I'm going to have some radius. I'll call this A. I'm going to have some distance here. This is what I care about. This is x. This is what I want to have things in terms of. And then I have R. Yeah, right triangles. I got to love them, right? So you may recall that with a right triangle, my hypotenuse squared is going to be equal to the sum of my two sides squared. Whoops, I should call this x squared. Right. So I can define my radius, or the distance to my charge. Now, well, here it's r squared, so this is going to be a squared plus x squared, where a is my radius. Right. So right away, I can do some things. So I can, the small amounts of finding my x, I'm going to have some constant times dq, I'm going to worry about that later, divided by r squared. Well, r squared is the same as a squared plus x squared. Right? Geometry. Okay, good. So now I've got a constant a and the thing that I'm changing, x, that'll be fine. And I can make sense out of this. Second thing is my cosine function. Well, I need to get that so that it's in terms of x because it's going to change. Well, here I am. I have a, x, and r. Right? So, but r is going to be equal to square root a squared plus x squared. And this is my angle. Remember, cosine is going to be adjacent divided by my hypotenuse, right? So, well, I can get my cosine function, my cosine of anything, cosine of theta, is going to be my adjacent divided by my hypotenuse, square root a squared plus x squared. So I'm going to replace cosine with this geometric function. We're going to do this a bunch, so this is going to show up in other places as well. So if I have my cosine, if my angle is changing, in this case my angle is changing as I change my value for x, I need to get it in terms of some geometric function like this, and this shows up several times. So I'm going to multiply it by my function for cosine, which is going to be this. I'm losing my pen. Pens. Here's a pen. Okay. So square root of a squared plus x squared. Okay. And now what I want to do is I want to add all these up, right? So what do I want to add all these up. So at this position x isn't changing. So at that position for x is constant. So I'm going to pull this out, right? So when I add up all of my dx's, right? So I'm going to get to my total energy in the x, or total electrical field in the x dimension, right? This is going to be the integral of k dq x over a squared plus x squared to the 2/3, 3/2. So, right? Adding one of these and a half from the square root, so I end up with 3/2. Well, the only thing is that's changing here is dq's, right? As I go around, so this is what I'm doing. I'm saying, well, I'm going to go around the circle. I'm going to add up all my dq's, right? X is constant for this position, right? So my x is not what I'm adding up. I'm adding up all of these dq's, right? Well, if I go all the way around the circle and I add up the dq's, what do I get? I get q. I get my total charge. So the nice thing about a circle, so I can do a simple integration, right? So this is going to be my x is going to be k times x over a squared plus x squared to the 3/2. There's the integral of dq, which is just q. So this is going to be kq times x over a squared plus x squared to the 3/2. Seems, oh, there it is. Seems a little weird, but let's think about the boundary conditions. Think about the extremes, right? So what happens when I get really far out here? So really far out here, that this is going to act like a point charge. So I should end up with kq over r squared, which in this case would be x squared, right? So when I get really far away, I should end up with kq over x squared. Let's see what happens with that. So when x is really big, a is inconsequential, right? So if I ignore the a, I have a really big x, what do I get? I get kqx over x squared raised to the 3/2. Right? So when I do the math here, I'll end up with kqx over x cubed. Notice my x over x cubed is going to give me kq over x squared. So I do end up having it act like a point charge when I get infinitely far away. Let's check when I get really close. When I get really close, I'm inside here. So if I put any charge here, this is going to be attracted or repelled equally in all directions. So at this position, it's going to be 0. Right, so let me think about that. Do I get 0? Well, when x is 0, I still have some radius, so I don't have 0 on the denominator, but with x 0, I get a 0 in the numerator, and this will come out to an electrical field of 0. Yes, I do. So, yep, seems to work. So anyway, my electrical field that I described for a circle of charge comes out to look like this. And we're going to come across this 3 halves things pretty frequently. And again, the way that we're getting there is we're using this geometric equivalency to replace the cosine function. And this way my angle is adjusted for how far away I am. So again, a simple integration, but setting it up was the trick with this one. And so what you end up with. Hope that helps. Talk to you soon. Bye.